Hello everyone. Today we're diving into advanced DDA. Our final goal for this session is to convert various statistical methods into Python's functions so that we could apply them to other datasets, like we did with our visualization functions. Now, we all have a consensus that our goal is to find features that allows us to determine whether this claim is fraudulent or not. And we need advanced statistical tools because we can't just visualize everything in our dataset. And even if we visualize them and see them with our naked eye, we can't guarantee that there's a significant interaction between variables. And in order to systematically understand our data, we need to slice and dice our data and then apply various statistical methods in order to view our data in different angles. Because when we look into our dataset, there are various types of variables. Some are numerical and some are categorical. But sometimes we want to compare numerical and categorical variables together. Or we also want to compare two categorical variables. For example, let's say we hypothesize that for detecting fraud, in our case insurance fraud, someone's age and the car's maker is an important factor. Then based on whether fraud was committed or not, we look at age, which ranges from 16 to 80. And this is a numerical variable. And the car manufacturer variable is a categorical one. So when analyzing variables like these, we need to be able to choose from the appropriate methods depending on the data's characteristics. So here are some of the methods that we're going to look over in this session. Assuming we have a certain level of understanding about statistical methods, let's briefly go over each one of them. So for these statistical methods, I've divided three different main key points that you should take away. The first one is the purpose of the analysis, the second, assumption, and third, mechanism. The purpose of the analysis helps you to understand why we need to perform this test and which kind of variables are suitable for this test. The second takeaway are assumptions. We need to understand the assumptions for each test in order to verify whether the test results is normal or not. The third takeaway is mechanism. For each statistical methods, we all need to know how they work because we want to apply statistical methods that are suitable for each scenario. Now, going on to the t-test, the purpose of the analysis is to compare the average of two numerical variables. To put it in simple terms, it allows us to check the average value of two different groups. Let's say we want to see if age is an important factor in predicting fraud. In order to do this, we split the data into two groups, those who commit fraud and those who don't. That would be group A and B on the right side of our graph. Then we compare two groups using a t-test. And here the null hypothesis is that the means of the two groups are equal, and the alternative hypothesis is that the average of the two groups are different. Here we want a conclusion that age is a major factor of determining fraudulent claims, so we want to reject the null hypothesis. But actually going into the t-test, we also need to check the assumptions. The t-test assumes that the two variables are independent and that the data follows a normal distribution. Essentially, it measures the difference between the two group means divided by each group's standard error. So the larger the value, the greater the difference between the means, and the smaller the p-value becomes. And we want the p-value to be small so that we can filter out features that allows us to distinguish a group that is fraud and the group that is not. Next is a Kolmogorov test. Similar to the t-test, it compares two numerical variables. The difference is that the t-test compares means, while the Kolmogorov test compares the distributions. We can say that it compares the whole dataset. So revisiting our example before, comparing ages of those who commit insurance fraud versus those who don't. The Kolmogorov test shows whether these distributions differ. So the null hypothesis and the alternative hypothesis is pretty similar here too. The null hypothesis hypothesized that the distributions of the two groups are identical. But the alternative hypothesis assumes that the distributions of the two groups are different. So here, we also want to reject the null hypothesis because we want to filter out some features that has different distributions, whether they are fraudulent claims or not. And for Kolmogorov tests, the assumption, unlike a t-test, there's no assumption of normality because we're directly comparing the distributions. And the underlying mechanism is that Kolmogorov test calculates the maximum distance between the two cumulative distribution functions. For example, take a look at the graph on the right, where x equals 1, the value of one CDF is 0.8 and the other is 0.6. These kind of gap is calculated for every x-axis. So it's calculated for x when x is -3, -2, -1, 0, 1, 2, and 3. And out of those differences, it uses the largest gap between them to check if there's any statistical significance. And if the p-value is below 0.05, we can conclude that there's a significant gap between the two distributions. Moving on to one-way ANOVA. We use ANOVA to compare categorical variables with numerical variables. The tests that I mentioned before, such as t-test, only handle two groups, but one-way ANOVA is different. It can compare 3, 4, or 5 or more groups at once. And here the null hypothesis states that all group means are equal. But the alternative hypothesis is that at least one group has a different mean. So if you see the graph on the right and perform a ANOVA test on the right, and if we reject the null hypothesis, it means that at least one group has a different average than others. For instance, we might examine how age varies by car manufacturer, and that means we can compare the age of the driver according to their manufacturer. So if we have an age column and a manufacturer column, we would divide the age column using the manufacturer column, such as Honda or other manufacturer. Then we would group those drivers and calculate the average and compare whether those average differs to each group. If at least one average differs, we would have evidence for a meaningful difference. But the drawback for ANOVA is ANOVA only tells us whether there's a difference or not, but it doesn't tell us which group differs. And this is where Tukey's honesty significant difference comes in. It's similar to a t-test, but it does multiple comparisons. If you have three groups, as an example, if you see on the right, we have three groups, then it would conduct different t-tests for A and B, between A and C, and between B and C. But running a lot of multiple tests can undermine reliability, because even if one test has a reliability of 95% confidence level, if we multiply 95% multiple times, this number would decrease, so the confidence level decreases. But Tukey's HST would compensate on the back end to consider those confidence levels. And by comparing each pair, it can pinpoint which groups differ from one another. So we can pinpoint which kind of level of car manufacturers are more significant to identifying fraudulent claims. Now let's talk about the chi-square test, which is suitable for categorical variables. Here, the null hypothesis is that the variables are independent. And the alternative hypothesis is that they're not. To check this, we first construct a table as if the variables were independent. This is the expected frequency. This is the table that you see on the right side, and it's on the front. Let's say we have two levels for two categories. For category 1, we have level A and level B. And for category 2, we have level X and level Y. So there would be 4 different combinations. And in the expected frequency table, we show how many observations will fall into each cell if features were independent. This table is created without looking into our data. In the actual frequency table, which is the one behind, we calculate how many observations actually appear in each combination of categories. This table is based on our data. Then we compare the observed frequencies to the expected ones. In our example, we compare the left top cells of each table, and if there's a significant gap, we reject the null, concluding that the variables aren't independent. And to give you some context, we can use chi-square to see if fraudulent occurrences is independent from whether the accident happened in the rural region or not. So instead of X or Y, we could have rural or urban. And instead of A and B, we would have fraud or non-fraud. And after conducting a chi-square test to compare whether the expected frequency of fraudulent claims happening in rural or urban, or non-fraudulent claims happening in rural or urban regions, we would end up with a p-value. And if the p-value is below 0.05, we could infer that there is some link between accident region and fraud. And now that we've introduced these kind of statistical tools, it's time to apply them to our dataset. So in our next session, we'll dive into the data and apply these methods.